Section: Introduction. In this section, we discuss how benchmarks significantly influence the field of artificial intelligence, AI. AI systems have made rapid advancements and are now used in critical situations, raising the need for these systems to be trustworthy and safe. Within AI safety research, various benchmarks have been proposed to measure important safety features, such as fairness, reliability, and honesty, which are separate from general model capabilities. We recognize that while it seems intuitive that these safety properties are not solely determined by a model's overall capabilities, these arguments often lack empirical support and can be countered effectively. This raises important questions about what constitutes progress in AI safety from a research and development perspective, how we can measure it, and how to differentiate it from general capabilities. The challenge lies in the fact that safety properties and general capabilities are closely linked. More advanced AI systems may reduce random accidents but could also pose greater risks if misused. Systems that align better with human preferences might avoid dangerous behaviors but could also be more capable, as humans tend to prefer intelligent assistants. This complex relationship makes it hard to identify specific safety improvements that stand apart from general advancements. Historically, there have been two main approaches to improving AI safety: alignment theory, which is a top-down method focusing on high-level risks, and a bottom-up approach that addresses existing flaws in AI systems. However, both methods can lead to safety washing, where improvements are misrepresented as safety advancements. In our paper, we propose a third approach by empirically measuring the correlation between common safety benchmarks and general capabilities across various chat models. Instead of relying on intuition, we calculate how closely safety metrics align with a general capabilities component that accounts for about 75% of model performance. A high correlation suggests that a safety benchmark may simply reflect general capabilities, while a low correlation does not necessarily indicate a benchmark's quality. Through extensive experiments, we find that many safety benchmarks do correlate highly with capabilities, which is concerning because AI safety research should aim to enhance safety beyond typical development paths. We also discover that the intuitive arguments from alignment philosophy can mislead researchers, as they often do not align with empirical data. Predicting which benchmarks are uncorrelated with general capabilities is challenging, highlighting the need for empirical measurement. We recommend that future safety benchmarks include their correlation with upstream model capabilities, ultimately clarifying the concept of AI safety as distinct research goals separate from general capabilities research. In terms of related work, we note that the development of benchmarks for evaluating AI models, especially large language models, LLMs, aims to define desirable model properties and guide development. While previous studies have explored various aspects of benchmarks, none have conducted a comprehensive analysis of safety benchmarks to examine their relationship with upstream capabilities. We also highlight that differential safety progress refers to advancements in safety properties relative to overall capabilities, with some methods achieving significant safety improvements without increasing general capabilities. This emphasizes the importance of steering AI development towards safer systems that diverge positively from the typical capability trajectory. Section Summary. In this section, we discuss the complexities of measuring AI safety, highlighting the intertwined nature of safety properties and general model capabilities, which can lead to safety washing. We propose a third approach that empirically assesses the correlation between safety benchmarks and capabilities, revealing that many safety metrics are closely linked to general capabilities, thus emphasizing the need for clear, distinct research goals in AI safety. Section: Methods. In this section, we derive a straightforward and broadly applicable method to assess whether a safety benchmark is linked to the capabilities of upstream models. For our experimental setup involving vision models, we utilize the accuracy of ImageNet as the measure of capabilities. We include a list of 63 adversarially trained models for vision robustness and 44 standard models for calibration in the appendix. We recognize that human values are the core beliefs that influence behavior and decision-making, and researchers often strive to incorporate these values into AI systems. We evaluate common benchmarks related to alignment, helpfulness, machine ethics, and bias, questioning if these metrics are mainly influenced by the capabilities of upstream models. Our empirical analysis addresses the issue of safety washing. We explore whether alignment with human preferences, as defined by standard benchmarks, is primarily determined by the general capabilities of upstream models. We provide context for understanding correlations, noting that the correlation between SAT and ACT math scores is about 81.5%. Similarly, we find a mean correlation of 74.4% among capabilities benchmarks for instruct-tuned language models. If safety benchmarks show similarly high correlations, they are not significantly different from upstream general capabilities. We consider correlations below 40% as low. Our examination of MT-Bench and LMSYS chatbot arena indicates strong correlations between human preference alignment metrics and upstream model capabilities in chat models. We observe a slightly weaker correlation in base models, with some top base models performing better on MT-Bench than many chat models. This suggests that alignment evaluations largely reflect upstream model capabilities, and the distinctions made between human preference alignment and capabilities may not be substantial. Despite this, many research labs still prioritize alignment as a safety-focused area, which can lead to safety washing without genuine safety advancements. We also note that enhancing an AI system's alignment with human preferences can be achieved by increasing its capabilities, raising questions about what truly distinguishes preference alignment as a critical safety research area. If safety-related edge cases persist with increased capabilities, they may not be adequately captured by current alignment benchmarks. Overall, we find a high correlation between alignment with human preference benchmarks and upstream general capabilities, making them susceptible to safety washing. In our analysis of machine ethics, we find that the correlation with upstream model capabilities varies by benchmark. One benchmark shows a high correlation of 82.2%, while another, Machiavelli, has a low correlation and minimal changes across models. We observe that sycophantic behavior worsens with increased capabilities in chat models, indicating a potential distinction between knowledge-focused and propensity-focused ethical benchmarks. Benchmarks assessing ethical knowledge likely measure underlying model capabilities and may also be avenues for safety washing. However, we emphasize that any benchmark's correlation with capabilities must be empirically tested rather than assumed. Finally, we analyze bias benchmarks and find low correlations with general capabilities, suggesting that improvements in these benchmarks may stem from factors unrelated to advancements in upstream capabilities. Some bias benchmarks, like Barbecue Disambiguated and Winagender, show high correlations but are often misused as safety metrics by developers. This highlights the need for caution in using safety benchmarks with high correlations to capabilities, as they can lead to safety washing. Overall, we conclude that the bias benchmarks we evaluated are generally not prone to safety washing. Section Summary. In this section, we derive a methodology to assess the relationship between safety benchmarks and upstream model capabilities, revealing that many alignment and ethical benchmarks correlate highly with these capabilities, which raises concerns about their effectiveness in ensuring safety and may lead to safety washing. Our analysis indicates that while some benchmarks are closely tied to model capabilities, others show low correlations, suggesting that not all areas of machine ethics are equally susceptible to safety washing. Section: Truthfulness. In this section, we discuss the concept of truthfulness, which is often considered essential for AI safety. Previous research emphasizes the need for advanced systems to provide truthful information, leading to the development of datasets focused on truthfulness and the verification of model outputs. By reducing inaccuracies, we can enhance the practicality and reliability of large language models for various uses. However, we question whether existing truthfulness benchmarks truly assess safety or simply reflect general capabilities. We analyze the correlation between truthfulness and capabilities, revealing that the performance of the truthful QAMC1 benchmark is largely influenced by general capabilities, with a correlation of 81.2%. In chat models, the results on truthful QA appear to be a rebranding of accuracy. While some may argue that chat models are less likely to repeat falsehoods compared to base models, we find that even base models show a significant correlation of 69.7% with capabilities. Notably, chat models exhibit a stronger relationship when we compare truthful QA accuracy to capabilities scores. Our findings suggest that we need better benchmarks to evaluate honesty in AI systems. The low correlations seen in other benchmarks, like sycophancy and Machiavelli, indicate that models may show dishonest behavior in specific situations, but current benchmarks do not effectively capture these tendencies. We believe that misconception benchmarks could be improved to better distinguish between genuine improvements in model honesty and general capability advancements. Next, we explore whether scalable oversight can contribute to safety. We find that datasets like GPQA serve primarily as capability benchmarks, with high correlations to general capabilities. This means that many scalable oversight methods are essentially repackaged strategies aimed at enhancing general performance rather than addressing specific safety concerns. The ambiguity surrounding AI safety can lead to misinterpretations, where improvements in capabilities are mistakenly presented as safety advancements, complicating the conversation around AI safety. We also examine the relationship between calibration and general capabilities. Our analysis shows that this relationship varies depending on the metric used. For instance, the RMS calibration error metric measures distinct phenomena, while Breyer scores across models correlate strongly with accuracy. We note that using Breyer scores to compare calibration across different models can be misleading, as it conflates accuracy with calibration. In summary, we find that the Breyer score is more prone to safety washing, while the RMS calibration error provides a clearer measure of calibration. Overall, our analysis highlights the need for careful consideration of how we evaluate truthfulness, capabilities, and safety in AI systems. Section Summary. In this section, we analyze the concept of truthfulness in AI, revealing that current benchmarks often conflate accuracy with honesty and may mislead safety assessments. We find that many safety metrics, including scalable oversight and calibration measures, are heavily correlated with general model capabilities, which can obscure genuine advancements in AI safety and contribute to safety washing. Section: Security. In this section, we explore the security of AI systems, focusing on ensuring they are not susceptible to harmful inputs or misuse. We examine two main areas: adversarial robustness and weaponization capabilities. We analyze whether current benchmarks truly measure unique properties or if they are closely linked to general capabilities. Our findings indicate that the correlation varies by benchmark. Traditional benchmarks, especially those related to text manipulation and adversarial examples, show a strong connection to the overall performance of current vision and language models. For instance, there is a parallel between the ANLI benchmark in language and ImageNet A in vision. While these benchmarks may have highlighted different aspects in earlier models, they now seem to reflect overall model performance. Conversely, we notice low correlations in benchmarks related to jailbreaking and gradient-based methods across both vision and language models. There is a similar relationship between the GCG benchmark in language and the PGD benchmark in vision. This highlights the potential pitfalls of relying solely on verbal arguments to assess whether a field measures distinct properties or merely reflects capabilities. Our empirical analysis reveals differing results between traditional adversarial robustness and jailbreaking benchmarks, despite similar claims of their uniqueness. This underscores the importance of empirical science over mere rhetoric. We conclude that some adversarial robustness benchmarks may be susceptible to safety washing, while others appear to measure distinct phenomena. Our results suggest that as AI models become more capable, their potential for weaponization also increases. The strong negative correlations we observe across various fields imply that advanced AI systems are more likely to have knowledge that could be misused. The inverted scoring system of WMDP benchmarks illustrates that higher scores indicate better suppression of harmful capabilities. As capabilities improve, safety researchers can concentrate on reducing weaponization risks. Generally, we find that benchmarks for weaponization capabilities are not prone to safety washing. We summarize our recommendations as follows. First, new safety evaluations should report their correlations with capabilities. Second, we should design benchmarks that are decorrelated from capabilities to encourage distinct safety advancements. Lastly, model developers must refrain from claiming improved safety unless they have made genuine progress and should avoid misusing safety benchmarks that are closely tied to capabilities. As new training methods are adopted, we must regularly reassess the relevance and adequacy of existing safety benchmarks and their relationship with capabilities benchmarks.